Ni hao. Hello. This is the 28th lesson in heat transfer. This will be the final lesson in the course and the final lesson in the unit on thermal radiation heat transfer. In this lesson, we will discuss absorption of thermal radiation by real surfaces, Kirchhoff's law, and the idea of the effectively gray surface. In the first part of the lesson, we will talk about absorption on real surfaces. By the end of this part of the lesson, you should be able to explain in your own words what the spectral and total hemispherical absorptivities represent physically for a real surface. You should also be able to estimate the total absorptivity from spectral data and information about the spectral nature of the incident radiation. While not listed here in the list of lesson objectives, I will also add that a key objective of this lesson is for you to recognize that the absorptivity of a surface is not only a property of the surface, but also a function of the nature of the incident radiation on the surface. This is very different than the emissivity, which is a true surface property. By the end of this lesson, you should be able to understand more what I just said. On with the lesson.
What about absorption? The absorption is going to be given by the spectral hemispherical absorptivity. So we have a spectral hemispherical value, just like we have a spectral hemispherical value for the emissivity. And it takes on kind of a similar definition. There's an analogy for sure between the emissivity and the absorptivity. But the difference is we're talking about a different process, right? So here, I'm thinking in terms of that surface, I have some incident energy, right? And I want to know what fraction of that incident energy actually gets absorbed, right, by the surface. So that's the absorption at this particular wavelength. So the spectral hemispherical absorptivity is defined as the ratio of that. What is absorbed at that particular wavelength relative to what is incident at that particular wavelength. The hemispherical has the same meaning. The hemispherical still means it's averaged over all directions. The spectral has the same meaning. It's at a particular wavelength. This thing takes on a value between 0 and 1. 1 if it absorbs all of the energy at that particular wavelength, and 0 if it absorbs none of the energy at that particular wavelength. That would mean that it's reflecting all of the energy at that wavelength away. By definition, the spectral absorptivity of a black body is what?
Now, what I would like you to do is pause the video and write down an answer to the question.
Aaron, it's just 1. It absorbs all. Right? Black body surfaces absorb everything. So it's going to absorb everything at every single wavelength. So again, just like with the emissivity, a lot of times we'll have spectral absorptivity data available. Actually, we won't even have absorptivity. Typically, we have reflectivity data available, but we'll get to that. So when I'm thinking about, if I want to get the total absorptivity, alpha, right, from the spectral absorptivity data, what am I going to do? We're still going to have a band approximation method, right? We still take advantage of that, but there's kind of an important difference between absorption and emission. We kind of do the same thing where I like imagining the spectral absorptivity data sitting on top of, so maybe it looks like this. Sitting on top of the incident radiation data. So maybe the incident radiation that looks like. That's G sub lambda. So if I want to get the total absorptivity, what I'm interested in is what's the net effect of what's being absorbed across all possible wavelengths. Right? What's the net effect of what's being absorbed across all possible wavelengths? So I have to go through, right, wavelength by wavelength, right? And I take the spectral absorptivity and I multiply it down by whatever the value of G sub lambda is at that particular, right, at that particular wavelength. And I got to go do this for every possible wavelength and add it all up, right? And that'll be what's absorbed. So when I do that add it all up thing, right, I'm integrating over all possible wavelengths, alpha lambda G sub lambda. And I want to know what is that relative to, right, what's coming in, everything that's coming in. So I integrate G sub lambda D lambda. So this is how we're going to get the total absorptivity. It looks, if you compare that, right, with the boxed equation on your handout, those equations look very similar, right? There is two differences. One, this has the absorptivity in it. And then the other important difference is it's not EB lambda here, it's G sub lambda, right? Absorption depends on the nature of the incident radiation. The value of the total absorptivity depends on the nature of the incident radiation. For the same surface, could be the surface of my writing pad, I could have a value of the total absorptivity to the radiation that's coming in on the surface right now of, I don't know, 0.9. And if I go and I put this in the sun, sunlight has a very different, right, spectral distribution of the energy. I could have a completely different value of the total absorptivity. So the absorptivity is not like it's a surface property, but it's not just a surface property, right? Because the same surface can have a different value of the absorptivity subjected to two different types of incoming radiation. So as much as it's a surface property, it's also a property of the radiation that's striking the surface. That's really, really important to remember and recognize. And that's different than the emission. So the emissivity is the emissivity. You know, the surface has an emissivity, it is what it is. But the surface can have an absorptivity with different values depending on the nature of the incident radiation. So you want to capture that down, which is like a really important observation. The total absorptivity depends on the nature of the irradiation. You have to know you have to know what G lambda is, right? You must know G lambda in order to do the calculation. You don't know what the incident radiation is, you can't say what the absorption is. Now, what's going to be nice is if the incident radiation is black body radiation. Because if the incident radiation is black body radiation, then you can make a substitution, right? If incident radiation is black body radiation, then G sub lambda is equal to EB sub lambda at whatever the temperature of the source is. Why is that helpful? Because now we can do we're still going to do the band approximation, right? In the band approximation, the alpha comes out of the integral. And now what I'm left over with is, again, fractional black body emissive power functions. And this handout applies. That makes sense? So you do the calculation exactly the same way. This works if the incident radiation is black body radiation. You just have to make sure that you calculate your fractional emissive power functions based off of the source temperature for the radiation and not the temperature of the surface. Really important that you understand what I just said. So I'm going to say it one more time. The absorptivity, the total absorptivity depends on the nature of the incoming radiation. It has G sub lambda in here, not EB sub lambda, like the emissivity definition. So it's complicated to do the calculation unless G sub lambda is some super simplified function, right? Like if G sub lambda is some easy to deal with function, then no problem, right? Then you can do these integrals no problem. But if it's not, then you hope and pray that the incoming radiation is black body radiation. Because if it's black body radiation, then you can make the substitution that G sub lambda is EB lambda, but it's at the source temperature, not the temperature of the surface. That's a really critical difference between the emissivity calculation and the absorptivity calculation. Here, the F function has to be calculated at the temperature of the source or of the surface. Here, the F function has to be calculated at the temperature of the source of the radiation. It's two different temperatures. So you're going to have two different F values for the F function. Oftentimes, like what we actually remember, you have to remember that there's a relationship between absorption and reflection. So for an opaque surface, right, whatever isn't absorbed has to be reflected. So a lot of times you might not see spectral absorptivity data tabulated. You might see spectral reflectivity data tabulated. That's because it's a lot easier to measure what's reflected than it is to measure what's absorbed by a surface. So imagine if you were in charge of figuring out what the the absorptivity of a particular surface is. You have to irradiate it, right? And you have to try to detect what's absorbed. That's really hard. A lot easier to irradiate it and look and see what's reflected, right? I can have a detector to see what's reflected. So in practice, what we often measure is the reflectivity. Once we have the reflectivity, though, we also have the absorptivity because they're related. Remember? So I think we wrote that down someplace earlier in your notes. This is a really important thing to remember.